So good afternoon, everyone. I am Aditya Nema. I am a final year PhD student of Pranab Sen. He is my advisor. So I'll be speaking on simultaneous decoding, unions, intersections, and a one-shot quantum joint typicality lemma on Pranab's behalf. Unfortunately, he couldn't be here. So for the rest of this talk, you can treat me as an epsilon approximate version of Pranab. Now, how good the epsilon is, it depends on how much justification I do to the talk. And this is the talk that is prepared solely by Pranab. And this is a single author work. So I'm here to present it. Okay. And the work is based on the two papers which are listed in the bottom. Okay. So the motivation for the particular talk is to study what is called simultaneous decoder for one-shot MAC by transmitting or for transmitting classical information through this quantum MAC. So the setting is as follows. We have a sender M, a sender N. The message for sender M is little m. The message for sender N is little n. We want to send the classical messages through a MAC channel. Now, MAC channel is a channel that takes in two input and gives one single output. Or it can be viewed as there are two senders and one receiver. Okay. So depending on M and N, we get the particular output state as tau Mn. So since the most of the talk will be quantum, even in the classical scenario, I'll be using quantum notations to be consistent. So what happens in traditional information theory is we want to transmit M and N reliably through a particular channel. And the criteria that we want is, or what I mean by reliability is, that the guess that I make at the decoder output, which is M hat N hat, the probability that M hat N hat not being equal to Mn should be small. Let's say we characterize it by a parameter epsilon, when M and N are chosen uniformly at random. So what we do is we fix the encoders M, that maps M to state rho M, that maps the state N to rho N. Now the two senders do their encoding independently. That is why the tensor product is there. And what I receive is the output state tau Mn. So Mn indicates the dependence of the output state on the input message. And then there is a decoding CPTP that gives me the guess M hat N hat. Okay. So we are interested in finding the one-shot inner bound or the rate region for this particular channel. So we want that the rate should be something like this. So this is analogous to the classical IID result. Oops. Okay. So the classical IID bound for transmitting classical information over a quantum MAC was given by Winter in 2001. So it says that R1, the rate region, so R1, just to make sure, is nothing but log of the cardinality of the message set M. R2 is log of the cardinality of message set N. So the rate region is as follows. R1 must be less than or equal to n times, so n indicates the IID thing. So it is n times mutual information between M and NZ. R2 should be the mutual information between N and MZ, and R1 plus R2, which is the sum rate, should be the mutual information between M and NZ. So this is the result in IID. So the natural one-shot analog is to replace the mutual information in the IID by the hypothesis testing mutual information. Now, we'll define that shortly, but this hypothesis testing mutual information was defined yesterday in the tutorial by Professor Millen. Okay, so let's see a particular decoding strategy. Yeah, okay. So this is known as successive cancellation decoding strategy in the IID case. So I can decode the blue point in the following way. So consider Z as the output. Okay, and the channel is between sender N and Z. So treat whatever we get from the sender M as noise. So the rate that can be achieved is the mutual information between N and Z. Similarly, now since we have decoded N, use it as a side information, club it with Z, and the rate that I can obtain by decoding M reliably is the mutual information between M and NZ. Let's call this as the rate point A. We can similarly achieve the rate point B by interchanging the roles of M and N. Now, the next question is how to achieve any point in between the points A and B. So I want to achieve the yellow point as shown in the slide. So the way to achieve yellow point is I'll be transmitting at rate pair A for alpha n channel uses and at rate pair B for 1 minus alpha n channel uses. Now the yellow point is nothing but a convex combination of the two. So this technique is known as time sharing. So I can get the entire rate region by time sharing and successive cancellation. Now what took a long way in generalizing the IID result to one-shot result is that in one-shot scenario, we do not have time sharing. Because the value of n is equal to 1, we are allowed to use channel only once. Okay, so hence we need what is called simultaneous decoder. So just as a warm-up, let's see how do we do this in the classical scenario. So in the classical scenario, M is mapped to rho m, which is a particular distribution. N is mapped to the state sigma n, which is nothing but another probability distribution, and the output of the channel is tau m n z. So the overall state I'm representing by tau m n z, which is a CQ state. So in classical case, it is nothing but the joint probability distribution of the 2 input to the channels and 1 output to the channels. Okay, so in this case, the desired one-shot inner bound is the hypothesis testing mutual information between m and nz, n and mz, and similarly for sum rate. Oh, sorry. Yeah, sorry. Okay. So let's define now what is the hypothesis testing mutual information. So the hypothesis testing mutual information is defined as, so I'll take maximizing over all the classical POVMs. The jargon in classical world for POVM is nothing but a hypothesis test. So what is a hypothesis test? A hypothesis test will map a sample point to 0, 1. In other words, it is a function that takes in a sample point m and z and gives the value between 0 and 1. Or another way to look at it from a probabilistic point of view is, when I get the sample point m and z, I accept it with probability little f of m and z. Okay. So the hypothesis testing mutual information is maximizing over all such POVMs such that the probability that I accept the correct hypothesis, which is the state tau m and z, should be at least 1 minus epsilon, and I want to minimize the probability that I accept a negative hypothesis test. So why is it negative? So what does m and nz partition means? So it means that I'm able to decode m correctly, but I'm able to decode n correctly, but I'm unable to decode m. So m factors out as the tensor product, and the remaining state is n and z. Okay? So this is the meaning of hypothesis testing mutual information. So just to recall, I want to find a maximizing f such that fm on tau m and z is at least 1 minus epsilon, and fm is such that the hypothesis testing mutual information is equal to negative log of fm on the negative hypothesis. Okay, so similarly, we have the hypothesis testing functions or the classical POVMs fn and fmn corresponding to the mutual information between nmz and mnz respectively. Okay, now let's see the sequential decoding strategy. So suppose m prime n prime was transmitted and z was received. Now what we do for decoding is we cycle through all the pairs mn in a particular order. Here it's the lexicographic order, except mn with probability f, m, n, and z. Okay? So if I happen to accept, I'll stop and declare that my guess for the received message is m, n. If not, I'll continue. Okay? If I reach the end of my list, I'll just say abort the protocol. Okay? Now, what is f? So we had 3 candidates in the previous slide. F is nothing but it is the classical POVM that is obtained by intersecting the POVMs fm, fn, and fmn. Okay, so in classical, we define this as the minimum of fm, fn, and fmn. So just to make sure what the definition is, so look at a sample point m and z, okay? Apply or obtain the value of f sub n sub m of m and z, f sub n of m and z, and f sub mn of m and z. Take the minimum. So do this for all possible points in our decoding strategy. Okay. So this gives the desired rate region in the classical domain. Now, we want to generalize this idea in the classical quantum domain. So what do I mean by classical quantum is that my input state or the message that I want to transmit is classical, and the output that I'll get from the channel is quantum. So what we do is we do, so both the senders, they encode their messages m and n to the states rho m and sigma n respectively. Since they are doing it independently, again, that is why there is the tensor product. And the overall state is a CQ state that can be written as tau m and z, with the distribution p being given to the message set m, the distribution q being assigned on the distribution n. So this is how I can write the CQ state in a canonical way. Now, so we'll consider the hypothesis testing mutual information. So this is the quantum analog of the classical hypothesis testing mutual information. So this was defined by Wang and Renner. So this is defined as follows. Again, maximize over all the quantum POVMs. So for this particular hypothesis testing mutual information, where the bipartition is between m and nz, so just to recall, m and nz bipartition means that I can decode n correctly, but not the message m correctly. So for this, what I'll do is I'll maximize over all the POVMs pi m such that I accept the correct hypothesis with probability at least 1 minus epsilon. So in quantum case, we all know probability is given by trace of the projector on the underlying state, and I want to minimize the probability that I accept the negative hypothesis. Okay. So pi m ranges over quantum POVMs on the state m and z. So without loss of generality, since we are working with a CQ state, I can assume that my POVM also has a CQ state. So what this means is that look at the contents of the register Mn, conditioned on that, apply the POVM pi sub m of Mn on Z. Okay. So similarly, define the optimizing POVMs for mutual information between n and mz and mn and z. So let us call those as pi n and pi mn. Okay. So now again we'll run the same sequential decoding processor, sequential but simultaneous. So it means we are trying to decode m and n in one particular task. We are not first decoding m and then going to try and decode n using m as the side information. Okay. So what we are doing here is, so again, assume m prime n prime was sent, we'll accept mn with probability trace of pi times tau of m prime n prime. If we happen to accept, stop and declare that mn was the correct guess. Okay, if not, continue. So this process can be analyzed via non-commutative union bound. Okay, but the question is, so in the classical setting, the decoding function f was the intersection or the minimum of fm, fn, and fmn. In quantum setting, what is that? So how do I make sense of intersection of projectors or POVMs? Okay, so I took the word projector because for our convenience, we'll replace all the projectors by all the POVMs by projector via Guelph and Neymar. So what is intersection of projectors? So let's say the projector pi 1 projects onto the space v1, projector pi 2 projects onto the space v2. So the intersection will define trivially as the intersection of the vector spaces v1 and v2. Okay, but in general, v1, the projectors pi 1, pi 2 need not commute. So I'll get the intersection as 0. So let's see. So the probability of k is 0 in this case is 1 minus trace of pi times tau. We can expand these two from the previous slide, and we'll plug pi mn as the intersection of pi m, pi n, and pi mn. So since these do not commute, therefore this particular the second expression in the RHS is 0. So I get the probability of k 0 is 1. So we fail. This is not good for achieving the rate region. Okay, so another attempt is, instead of considering the intersection, let's consider multiplying all the POVMs. So the decoding POVM pi or the intersecting POVM pi is the product of pi m, pi n, pi mn, and pi n, pi m. So it can control the case 0 via gentle measurement lemma of Winter. But let's see what happens in case n. So initially case 0. So case 0 is that the transmitted message was m prime n prime. I happen to come across the pair m prime n prime, but somehow I am not clever enough to accept that. Okay. So in this case, let's see what happens to case n. So case n, just to recall, means that I am unable to decode n correctly, but I am able to decode m correctly. So in this case, the probability of case n is given by trace of pi times tau n tensor tau mz. Plugging the value of pi from above, which is the product of POVMs, I get this. Now the last quantity there, which is pi m acting on tau n tensor tau mz. I don't know what this quantity is. Had it been pi n times tau n tensor tau mz, and if I take the trace, then I know that is upper bounded by the 2 to the minus hypothesis testing mutual information. So in this case, we don't know what this quantity is. So we fail again. Okay. Now let's try and go back to our old viewpoint where we are taking intersection of the vector spaces, but in a different way. So let's say V is nothing but the span of V1 complement, V2 complement, and complement of the span. So this is same as V1 intersection V2. Now, how V1 intersection V2 equal to 0 manifests itself in this setting? So since V1 intersection V2 is equal to 0, the span of V1 complement and V2 complement is nothing but the Hilbert space H, the whole of the Hilbert space H. This leads to an analogous phenomena, to an anomalous phenomena. What is the anomaly here? Okay. So I project onto the V1 complement the right state tau with the correct probability, that is, the error probability in this case is upper bounded by epsilon. Similarly, tau, so this is from the definition of the hypothesis testing mutual information, that trace of tau times V, tau times pi on V is bigger than equal to 1 minus epsilon, Therefore, trace of tau times pi on V complement is less than equal to epsilon. Okay. So let us look at this case. Now, since V1 complement union with V2 complement is H, therefore this term is 1. So this is the anomaly, that I cannot project with high probability on V1 complement nor on V2 complement, but I am able to project with high probability on V1 complement and V2 complement union. Well, is this possible? Yes, it is possible. It is what is happening unless epsilon is equal to 0. Okay. So let's see what is the culprit behind this anomaly. The culprit behind this anomaly is nothing but the small angle between the spaces V1 complement and V2 complement. Okay. So how do we get about this anomaly? So this is the first idea, which is known as tilting. So what we do is we try to tilt V1 complement and V2 complement in two orthogonal directions. Okay. Let's see how do we do that. So that cannot be done in the original Hilbert space H. For that, I need to extend my Hilbert space H in the following way. So what I'm doing is I want to tilt. Oops. Okay. So I want to tilt V1 complement, let's say in a direction Y with some small angle. I want to tilt V2 complement in a direction that is orthogonal to Y, let's say Z, with some small angle. So how do I do that? So I'll define the tilting operator T1 as the operator that maps H to H1, tilting operator T2 that maps H to H2, and the extended space H tilde is the direct sum of three isomorphic and orthogonal spaces H, H1 and H2. Okay. So what do I mean precisely? So when I tilt along the direction 1 with a parameter alpha, it means that tau 1 alpha is an isometry, which is given by under root 1 minus alpha times IH. That is, with probability 1 minus alpha, I remain in the same Hilbert space H, and with probability alpha, I go in the tilted direction. Okay. So what this kind of definition or this scenario buys us is the following. So this is something that we call as vanilla tilted span. So what this means is, so let us consider a state V in H. So in our running example of MAC, this V is nothing but the state tau. So if I project V on pi and succeed with probability at most epsilon, okay, so pi I is the projector such that trace of pi I times ket V bra V is less than equal to epsilon. And pi I prime, let this be the alpha tilt of pi I in the ith direction, which is given by the above definition. So in the above definition, if I ask what is pi 1 prime, it is nothing but substitute I equal to 1. Okay. So let pi prime be the span of pi I prime in H hat for all I. So this is nothing but union of pi I prime for all i's. Okay. Then we have this theorem. So the probability that I succeed by projecting V onto pi prime, which is the union of the tilted projectors, is lower bounded by 1 minus alpha times epsilon. This can be proven by using these definitions. And the surprising part and the more useful part is that the upper bound is given by 1 minus alpha over alpha times n epsilon. Now this is reminiscent of the good old classical union bound, but with the parameter not 1 times n epsilon, but 1 minus alpha over alpha times n epsilon. Now this gives a way to do union of projectors as mentioned in the title. So this already improves the result of Anshu, Jain and Varsi for compound channel. And we believe that it should have more applications in quantum information theory and quantum communication complexity. Okay. So we have this particular result, which we say is nothing but vanilla tilted span. Now let's see whether we have a handle over case 0 or not, because this is the one that went for a toss. So probability of case 0 is given by this expression, okay, and this can be simplified to 1 minus 1 plus this particular quantity. So I get this is direct linear relationship between epsilon. That is, probability of case 0 is less than equal to 1 minus alpha over alpha by 3 epsilon. So if we plug in alpha to be equal to half, we recover the classical probability that we would get in case 0. Okay, so case 0 is solved in this case, but let's see what happens to the other cases. So let's find out the probability of case m. So in case m, so this is the probability expression. When we expand this, we get this particular equation. Okay, and for this, now I need to use the lower bound, with epsilon being replaced by 1 minus 2 to the minus hypothesis testing mutual information. So this can just be seen by interplay of projecting onto pi and pi complement. So it will just follow by the definition. So, and since alpha is non-zero, because if alpha is 0, this union bound doesn't make a sense. This particular term becomes infinity. Okay. So we fail yet again. Okay, so we have a handle over case 0, but not a handle over case mn and case mn. So it's like a balloon. We try to push something from one side and the things come out from the other side. So let's see what further we can do. Okay, so this brings us to the new idea number 2, which is smoothing and augmenting. So far we have been tilting only the projectors. Now we'll tilt the state as well. So tau was our initial state. So what we'll do is we'll tilt it simultaneously along orthogonal directions mn, m, and n. So what do I mean by tilting the state? It means look at the state tau mn, look at its component along the direction mn, m, and n, and take the linear combination of it. Now the parameters in the linear combination, they have to be chosen very carefully. So that comes out by a lot of hard work that is done in the paper. Okay. And what does this buy us? Okay, so if I try to marginalize one state, remember in the case m, tau m fall out as a marginal factor. So it means it is equivalent to averaging out the other direction. So, okay, speaking intuitively, what is happening is if I look at the state tau mz, which is marginalization of the state m, so it gives me a particular state that is tilted mostly along m, and it averages out all other directions. So what does mostly mean? Mostly means that tau mz is a convex combination of two states, the first being tilted solely along m, and the second, which is the error part, which has small Shetton L infinity norm. So this is another catch, that whatever junk I am getting has small Shetton L infinity norm. So how do we make sure of this? So this can be made sure only when the distribution Qn has high min entropy. Now min entropy and L infinity norm are related. So how? So yeah, just to make clear. So the min entropy of a particular quantum state is nothing but negative log of the maximum eigenvalue of that underlying state. So that is nothing but the Shetton L infinity norm. Okay. But wait, so PQ was fixed a priori. Okay. So what we do is, the another idea which is known as augmenting. So augmenting means we have the initial encoded state rho m. Okay, we augment it, or we take its tensor product with a maximally mixed ancilla of dimension L. And the dimension L should be large enough so that the min entropy is under control. It is high enough. Okay. So now finally what we have, so we take the state tau, we first augment it with the ancilla along m and n separately, and then we tilt it along this direction. So it turns out that this particular tilting of the state works for the case mn, m, and n. Let's see how. So for this, we'll also need to define what is our tilting projector. Okay. So what is pi tilde m? Okay. So look at the good old projector pi onto the space V1. Take its complement in the good old Hilbert space H. Okay. Now tilt that pi complement along the direction H1 and look at it in the extended space H tilde. Now take the complement of that tilt. Okay, and we are calling that as pi m tilde. Similarly, do this for pi n tilde and pi m n tilde. Now, the intersection of the projectors in this is nothing but the intersection of the subspaces or the vector spaces, okay, which we are calling it as pi hat m and z. Okay, now let's see what this buys us. So probability of case m is given by this expression. Now smoothing and augmenting, it tells me that this tau m is tilted mostly along m. This tau n z is tilted mostly along n. And this pi hat, by this particular tilting, so it is a non-trivial result. So that also can be seen in the paper. So this expression will more or less disassemble itself into trace of pi m along direction m times trace of pi nz along direction tau nz, and we have all these quantities under control. Okay, so let's carry on with the calculation. So since pi hat is nothing but the intersection of these three, so pi tilde m is a superspace of the space of pi hat. So I can retain this equality by bringing in pi tilde m over here. Now since pi hat m is less than equal to identity, so I have this particular equation, my probability won't increase. So this is trace of pi tilde m times tau prime m tensor tau prime nz times pi tilde. Okay, and as mentioned earlier, that smoothing and augmenting gives me a convex combination of two states, which is the tilt along the right direction and a tiny jump. So it turns out this can be proven through very simple calculation, that this is upper bounded by 2 to the minus hypothesis testing mutual information between m and nz. Okay, so like this we have a control over case m, case n, and case mn. But for case 0, unfortunately, still this is not good enough. But So what we have not done is we have not done a particular tilting for pi tilde. So first we did augmentation and smoothing for the state tau. What is left is to do a similar kind of analysis for the projector pi as well. So that is known as the matrix tilting. So this is another non-trivial thing. So the matrix of tilting parameters, it should respect some partial order on the subsets. So this can be used, and what we have is, we have the matrix tilting of the tilted projector pi tilde. We have the matrix tilting of the states, which is the original state, augmented with the maximally mixed ancilla, and ultimately we have all cases under control. Okay, so we wanted to find the capacity of this particular MAC. So instead of this, we'll work with the perturb channel C prime. What is perturb channel C prime? Look at the encoding of M on rho M, augmented with this ancilla, so this should be here. Similarly, do it for the case N. Okay, and the state that I get is tau prime. Now, thing to note is that the state tau prime is very close to the original state tau tensor I over L tensor 2. Okay, so this gives me the desired rate region, but the error parameter won't be epsilon now, it is epsilon to the 1/4. Now, once I have the rate region for the perturb channel, this rate region holds for the original channel as well with slightly increased error. So in the perturb channel case, the error parameter is 10 epsilon to the 1/4. So in the original channel, it will be 11 times epsilon to the 1/4, slightly more. Okay, so how deep can we push this idea? We have considered the idea of tilting or unions and intersection of projectors only for a 2 sender, 1 receiver MAC. We can do this for more than 2 classical senders and more than 1 quantum output. We can do conditioning on the classical systems with this particular idea, and everything would go through. So there is no new idea required when we increase the number of classical systems, except that we have to do matrix tilting along the directions which are indexed by a lattice of so-called pseudo subpartitions. Okay. Then, so, and another application of it can be, so in multi-terminal coding, intersection is followed by union. So which is termed as union of intersection. So we know how to do intersection, we know how to do union via the vanilla tilted span theorem. Okay, so this is required in inner bound proofs of non-unique decoding. So what does non-unique decoding means? So in multi-terminal setting, what we want is, we do not want to recover the message string uniquely. We are happy to recover that string up to certain sets. So for example, this happens in Martin's inner bound. So one can look up in Al-Gamal for the details. Okay, and the author has applied these ideas into another paper which was mentioned on the first slide, to come up with one-shot inner bounds for sending classical information through unassisted and assisted channels like MAC, Martin's inner bound with common message for broadcast channel, which was not known even in the IID case, and Han Kobayashi and Chong Motani Garg Al-Gamal inner bounds for interference channels. Okay, so to conclude, what we have powerful tools to handle unions and intersections in packing type arguments. So where are packing type arguments required? When we want to do channel coding. So channel coding means I want to transmit classical information through a multi-terminal channel. It may be unassisted or it may be assisted. Assisted means that there's pre-shared entanglement that is allowed, and assisted means there's no pre-shared entanglement. So what is open is, so how about unions and intersections for the covering type arguments? Now covering type arguments, they cover the lot of the source coding problems. So the best known result for source coding problems is the convex split lemma by Anshu and Jain. And this makes use of pre-shared entanglement. So this is not an unassisted result. Okay. So the author has some non-trivial results under this covering type scenario also, but they are not good enough currently to obtain simultaneous smoothing. For example, we cannot recover the quantum 2 sender 1 receiver source coding problem, which is also known as quantum Wiener-Zipf problem. Now, how about union and intersection? In the packing type arguments, for when the negative hypothesis states, they are not of the form of tensor product of marginals. Like if the negative hypothesis is not of the form like tau m tensor tau nz, if it's a joint state. Okay, so this is another interesting open problem to pursue. Okay, so thank you for your attention. On a serious note, I would like to thank QIP for allowing me to present my advisor's work. And also I would like to sincerely thank my advisor for entrusting me with this opportunity. Thank you.